F of 2 equals 3 is it's a point. We know that we have the point 2, 3 on our function f. F prime of 2 equals 1, negative 1, excuse me. What does that give us? So we know our slope is negative 1. Colby, what is our tangent line equation?
1 minus 3 equals negative 1 times 3x.
Tangent line equation. Okay, if we want to approximate f of 2.5 without knowing any other information about f, we can plug it into our tangent line. Hmm? 3.5? 2.5? Oh, that's kind of weird, huh? So f of 2.5 is approximately 2.5. Okay, that's something we've done throughout all of our units, really. We talked about tangent lines in Unit 1. We really talked about them once we knew how to take derivatives in Unit 2. Okay, today we are going to talk about tangent lines again. Okay. But you're going to hear kind of some different vocabulary with it. So we're going to talk about kind of the different ways you may be asked to write a tangent line and what we can do with it and how does that relate to derivatives. Okay. So I'll let you go ahead and get organized for notes. Quizzes we'll look at towards the end of the hour. Where did I put my notes? I don't know what I put this. Okay. Okay. Just a disclaimer, if you have friends in Mr. Griebel's class, I think he might teach these last two sections in a different order. So what we do today, I think they do Monday and vice versa. So just throwing that out there. I like it this way, he likes it the other way. So we do it our own way. When you see the word linear approximation or linearization, just combining it all into one word, linearization, linear approximation, they all mean, hey, write the tangent line to help you. Okay. Sometimes we don't know information about our curve, but we know but we can find the tangent line. And so if we don't know, the equation of our curve, or we don't have a way to get it, then we can use the tangent line and move away from that point just a little bit, and we can approximate fairly close to what the y value should be. Okay? So like, here's a tangent line equation, and this is what we just got done doing, right? Our slope is the derivative at the point. We have a point, and as long as we have point and slope, we can write the equation of a line. Okay? This is what you just did in your warm-up problem. Okay? And the point of it is, we know that XY coordinate on the curve. Okay? If we maybe don't have a way to figure out what these other coordinates are, we at least can move away a little bit. The y value on this tangent line isn't the same, but it's very close, so we can approximate the y value of the curve using that blue tangent line. Okay? And that's the concept that we're going to be working with today. Is there going to be error? Yes, but hopefully we can keep it minimal by staying close to that coordinate, right? The closer we stay to that green coordinate right here that I pointed out, the closer we stay here, the closer our approximation is to the real thing. Okay. Did you have a question, Colby?
Yeah.
Oh, okay. You were like, it looked like you were like looking for something. Okay. So find the linear approximation of the square root of x at x equals 4. Okay, we're going to start very basic. When you see the words linear approximation, that means tangent line. And for a tangent line, we need a point and we need slope. Okay? In calculus, our slope is going to come from the derivative. Okay? So first of all, let's start easy. Where did my of go? See how like my of got cut off? I don't know where my of went. It's strange. Like it's right here, but it's not showing up on my slide. There's something else there that's covering it? Okay. What's the y coordinate? How did we get that? The square root of x. The square root of 4 is 2. Okay, find the derivative and plug in 4 for me, please. Lauren, what's our derivative?
Half x to the negative half.
Okay. So when we plug in 4, Nick, what do we have?
1/4.
Do you agree? So if we are going to write the tangent line equation, Turner, are you good?
Yes.
Okay. We're going to write our tangent line equation. We have y minus y equals slope times x minus x. Okay. Now, just a fair warning, the back of your book will probably solve for y. So they will probably have 1/4 x minus 4 and then add 2. I am fine. I like you to keep it in this form. I just don't want you to be surprised when the back of the book does this. Okay? I like this form. I would accept this form too. They're both fine. Okay?
So we don't need to distribute like the 1/4.
No. It actually makes it easier when you leave it like this. Like in our warm-up problem, it was really easy to take 2.5. Okay. It was really easy to take 2.5 minus 2, right? So it's better to not distribute so you can approximate easier. Okay. Okay, so what are we going to do with it? Let's say we don't have a calculator. Okay, we usually do. Let's say we don't. The square root of 4.02, that's not something we just know off the top of our heads. We know that the square root of 4 is 2, but the square root of 4.02, like, we don't know how to do that without a calculator. But we have the linear approximation of the square root of x at x equals 4. Would you agree that 4.02 is fairly close to 4? Okay, so we are basically going to approximate f of 4.02, since 4.02 is under the square root and our function is square root of x. Do you see that relationship? Like f of x was square root of x, so our x value is 4.02. Okay. I thought I heard a wait.
Yeah, I did.
Okay. So you okay? Okay. So if we have y minus 2 equals 1/4 times 4.02 minus 4. Oh, excuse me, I didn't want to plug that in yet. This was the tangent line equation from previous. We can throw in 4.02 for x to approximate what the y value would be. What is 4.02 minus 4? And if we take 0.02 and we divide it by 4, what? Because it's basically like 2/4 times 1/100. 200 divided by 4. Okay. So our approximation would be 2.005. What we just did is we said, okay, f of 4.02, which is the square root of 4.02, is approximately 2.005. What? I am making a point, but I would at least want that part of it. Okay. Plug that in. Who has a calculator out? Somebody has a calculator out. John, take the square root of 4.02 for me. Well, actually, don't do that yet. Don't do that yet. Can we do it next? Sorry. Don't press enter. Okay. We have to do something first. Without entering it into your calculator, we know if this is an over approximation or an under approximation. It's not exact. Remember, we approximated. Is it over approximated or is it under approximated? Take about 30 seconds to discuss it with your pod. How would we know if it's under or over without typing this?
I would guess. Too high or too low?
Okay, here's our curve. F of x equals radical x. Do you agree with that curve? Here at the point 4,2, we wrote the equation of a tangent line. Where is that tangent line sitting? Above our curve, because our curve has what property? Because it's concave down. Okay? Since our curve is concave down, our tangent line is sitting above our curve, which means our approximation is too much. Okay? So 4.002, excuse me, 4.02 would be like right there. That's not very accurate, but I'm trying here. And we used our tangent line approximation to do it. So we could approximate it without a calculator. Sean, what's the exact value? 2.0049 blah, 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 blah. Okay. Now, could I use that tangent line to accurately approximate the square root of 10? because 10 is not close to 4, relatively speaking. Okay? Yes?
Will we always be able to like see the graph to know whether our tangent is going to be above or
No.
below?
No. So that's when you're going to have to think about the concavity of the function. So we know that like our first derivative is 1/2 x to the negative 1/2. Okay? If we were to find our second derivative, we would have negative 1/4 x to the negative 3/2. Okay, well, what's true about our second derivative? It's always negative. Now, that's not always the case. Think about plugging in the specific coordinate. So if I talked about the second derivative at our coordinate, it would be negative. So we're concave down, so our tangent line is sitting above it. What happens if our second derivative is positive? We're concave up, and where's our tangent line? Below it. Okay. Okay. So your first few problems of your homework, some of them will look like this, and some of them will be very straightforward, like write the tangent line equation. Okay. We're going to talk about the concept of differentials, which still is a tangent line equation. We're just going to do it in kind of a different manner. So I'm going to give you a moment to copy down this picture, and we're going to talk about what this picture means. Okay? So there's x and x plus delta x. There's dx, delta x, dy, and delta y. Sorry. dx equals delta x. So A is the coordinate in which we would write the tangent line equation for, because that's where the line and the curve are intersecting.
And what's D marking on that?
D is more marking the change in x over. Like it's at, we haven't changed our height yet. We've just changed our x. So we went,
Capital D's?
yes. I am not too worried about the capital D, capital B, capital C. Okay. A is the coordinate of importance right now. Okay. So what's happening? We have a blue curve and we have a pink tangent line. Okay. We're about to go through how to use differentials. Okay. All it is taking a tangent line equation without actually having to write the tangent line equation. Okay? So first of all, dx and dy. Where do you see those two-letter chunks? Derivatives, okay? So we see derivatives as dy dx, right? That means derivative. Which means what? Okay? dy dx is the slope of the tangent line. So when you see dx and dy, they're describing the slope of the tangent line. Okay? Delta x and delta y, what does delta stand for? Change in. So delta x and delta y are describing the actual change in x and the actual change in y. Okay? So you see that here's delta x and delta y. When you follow delta x, delta y, we get to our curve. Okay? But if we go over dx and up dy, we're on our tangent line. Okay, do you see the difference? Okay. Dx and delta x are always going to be the same. The difference comes with the change in y and dy. Okay, the change in y is the actual change in y, but dy is that change along the tangent line. Okay, that's calculating the slope on the line. Okay. I have a list of instructions on the next page. I'm going to go ahead and just give you an opportunity to write things down before we actually talk about things. Okay? Does that sound okay? First of all, are there questions on this picture before I go? Okay. We're essentially going to use our tangent line equation to approximate like we did earlier. We're just going to do it with dy's and dx's and delta x's and delta y's, and I'll show you how to put it all together. Okay? Oh, I do have a screen slide. Okay, so write differentials. Oh, and it changed to blue. I don't know why it keeps cutting things off. Okay, so delta x equals dx. That's important. It's also kind of like a weight off your shoulders. They're one and the same. They're interchangeable. Okay, so let me tell you a little story about my computer. We got new computers, right, over the summer. And so, like, the software that I use to do these notes on the smart board, we had to get, like, a new program of that. And so sometimes I open up my smart notebook files, and they look different from what they should. So this is what I would write down. Delta y is the actual change in y. I would probably just stop there. Just underline what I have in red. Okay. Delta y is the actual change in y. Morning, Mr. Spoker.
Hello.
And then dy is the change in y of the tangent line. Okay, just like we talked about in that picture on the previous slide. Delta y is the actual change. Dy is the change in the tangent line. Agree or disagree? F prime of x is the same as dy dx. Okay. In this picture that I talked about on the previous slide, I've been separating dx and dy, right? In our picture, we have a dx calculation and we have a dy calculation. We've never seen them separate, but we can do that. Okay? So if I separate dy and dx, I could put the dx over with the f of it, f prime of x. Okay? So what I need you to write down is that dy equals f prime of x dx. We're going to use that to calculate just the dy piece of our picture. Okay. Now I keep telling you dy is different than change in y. dy is different from change in y. But what would happen if we actually didn't have a change in x? Would dy and delta y still be different? If I don't actually move away from the tangent line, are those values going to be separate? Okay, let's go back to the picture. If I stay at this point, would dy and delta y be any different?
No.
The y value on the tangent line is still the same as the y value on the curve. When we move away from it, when we actually have a change in x, that's where they begin to separate. Okay? So if, for some reason, delta x is 0, then dy and delta y would be the same value. Okay, now I know that we've already done the approximation of the square root of 4.02, but I would like to show you how it works with this differential method. Okay? The biggest piece is this right here. dy equals f prime of x of dx. That's how we're going to begin our differential problems. Okay? So let's go back to the tangent line equation problem that we did from before. There. Okay, we have f of x is radical x. Okay. Change in x is 0.02. That means we're going from 4 to 4.02, right? Just like we did in our tangent line problem, but we're going to call delta x 0.02 because that's the change, that's the difference in our x values. Okay? So if delta x is 0.02, what is dx? 0.02. Okay, they're one and the same. Okay, which means dy is f prime of x dx. So we're going to have to calculate the derivative, which we've already done, and then throw in our values for f prime of x and dx, which we know. Okay, so from our first example, f prime of x was 1/2 x to the negative 1/2. Okay, so we can replace that. But since we're going at x equals 4, we can throw 4 in there, and then we know our delta x is 0.02. Okay? 1/2 times 4 to the negative 1/2. What is that? 1/4. We calculated that earlier. 1/4 times 0.02. Right. What did that just tell us? Well, what did we find? 0.005. What does that represent? Change in y. Okay. So what's the y value of our original? 2. So f of 4 plus our change, so here's our x value with the change in x, is approximately our y value plus our change in y. Tangent line equation without actually having to write it. Turn, did you have a question?
So, I know we found that another one, but like, how do we that this way? Like, the f of over 3, like, was there like a...
Okay, so all I did here was we started at x and we moved over 0.02. So that means our x value is now 4.02. We started with a y value of 2 and we changed 0.005 positively. So now we're at 2.005. Okay?
Would there be any instance where it would like, you would subtract it? Like,
Yes, if this was negative,
oh,
then you would subtract it, because then we'd have a negative change. Okay? But if we go back to our picture here, okay, like this was essentially the coordinate for 2. Delta x was 0.02. Delta y was 0.005. So now we're at the coordinate 4.02 to 2.005. Okay? Still an over approximation because of the concave down. All right. How about there? How about you at your table work together and try this one? So all it says is without graphing, find dy for y equals 4x cubed minus 1. I'm giving you x equals 1. I'm giving you delta x, which equals dx, is 0.01. Just calculate me dy. But I don't want it to be quiet in here because I want you to talk to each other about it as you do it. Okay? Thank you. You too.
Oh, I times like 12. Yeah.
Right. First of all, and anything times 1. Okay, what's F? Okay, first of all, is this your first step? Is this your first step?
Yes.
Yes, thank you for the confirmation. Your second step, dy equals, Rebecca, what's f prime of x?
12x squared.
12x squared dx. Okay? Well, 12x squared evaluated at 1 is, everybody?
12.
Whoa. Thank you. dx is 0.01. So our dy is 0.12. Okay. What does that mean? That means, well, if f of 1 is 3, then f of 1.01, because I added my change in x, is approximately 3.12. Yeah. Okay. Last example, you ready?
Yeah.
Propagated error. Okay. Use differentials to approximate the error in computing the volume of a sphere. So write volume of a sphere. If the radius is measured to be 10 centimeters with a max error of plus or minus 0.2 centimeters. What is it?
What?
What is it?
The volume of the sphere.
It's cubed because volume is in cubic units. Okay. Okay, so essentially, let's see, what did they give us? They gave us the radius is 10. What is this? That's the delta. We like to think of it as x, but r is kind of acting like our x right now. Would you agree? So I'm going to call this delta r. Okay. V is kind of acting like our y. Do you agree? Okay. So instead of dy, I'm going to write dv. What do we write right here? The derivative, which would be 4 pi r squared. And then, so it's usually dy f prime of x dx. But instead of x, we have r.
So how can we overcome like the r?
Because we are not taking the derivative with respect to time. Technically, we're taking dv dr, and we're just separating the dv and the dr. Okay? Kind of like over here, like taking dy dx, and then we move the dx. Okay, so dv equals, I told you that our radius was going to be 10, and our dr was plus or minus, 0.2, not 0.2. Too many zeros. Okay. What's 4 times 100? Times 0.2? So our volume could differ by 80 pi cubic centimeters, whether that's more or less than the actual value. Okay? So, science class, percent error. We have a fraction, right? We are going to take 80 pi. That's going to be basically our error in the actual volume. So what should we divide by? The actual volume, okay? You need to take error over actual to get the percent error, okay? So our actual volume would be 4/3 pi r cubed. I'll just do the calculation. So, did we do anything different than the slide before? We didn't. It is worded different, and then I just went one step further. What would be the percentage error? And so for percentage error, we took our error over the actual amount. Okay? All right, I do want you to, yes. Yes. You wouldn't necessarily need